Hey everyone, this is our last video for the related rates series of videos. So this is, I think, part 5, but it's our last one, and I left the best for last. This is one of my favorite related rates problems to do. So at the Dodgers Braves game, Urias threw a 90 mile per hour fastball. How fast does the batter need to turn his head, his eyes really, right, to keep his eye on the ball? So as the batter is watching this, right, we're expecting the ball, and the ball leaves the pitcher's hand. So how fast do his eyes need to move to keep his eye on the ball and be able to hopefully hit the ball? And we want to know how fast he can turn his eyes when the ball is 1 foot away from the pitcher. Note that a batter stands 2 feet away from the home plate mat at bat. And so let's take a look at this. So a ball moves at 90 miles per hour. So that was the fastball that was thrown. And so one of the things I want you to notice in this problem, we do need to go through the steps, right? Like draw a picture with variables, identify your d what, but let's read it again and identify the units. So I really want you to pay attention to the units. So read it again, maybe pause the video. What do you notice? And some of the things that I hope you notice is that we're given that Urias, this is from the Dodgers, Julio Urias, he threw a fastball at 90 miles per hour, right? But then notice that we want to know how fast the batter needs to turn his eyes to keep his eye on the ball when the ball is 1 foot away from the pitcher. So I want you to notice the unit difference, right? This is in 90 miles per hour, and this is given in feet. So we're going to need to be consistent. Either you turn the 90 miles per hour to feet per hour, or you turn the 1 foot to a fraction of a mile. So we need to make that decision as we set up the problem. I'd like us to convert the 90 miles per hour, in fact, to feet per second. And why per second? Well, we're talking about keeping the eye on the ball, so it's kind of hard to monitor that in an hour base. But when you throw a fastball or a lot of things like that are measured in miles per hour, but we want to convert it to feet per second because we want to be able to see how fast do your eyes essentially need to move, and that's easier to keep track of in a per second basis. So let's convert 90 miles per hour to feet per second. So we're going to do some dimension analysis here. So 90 miles, we're going to convert that to feet. So we know 1 mile has how many feet? 5280. And if you're not sure, you can look that up. And then 1 hour has 60 minutes. And then so how many seconds is that? So that will be 3600 seconds. Right, 1 hour has 60 minutes, 1 minute has 60 seconds, so that's 3600 seconds. Computing that gives us 132 feet per second. So our 90 mile per hour fastball became 132 feet per second fastball. All right, so now that we've converted that, let's go back and read the problem. I did change the 1 foot to 10 feet just to make it a little more realistic, because as I was thinking about this problem a little more, it's like, well, by the time the pitcher does his move of throwing the ball and extending his arm, 1 foot is just not that realistic. So let's do 10 feet away from the pitcher. And so I edited that in here and in your notes. So go back and check the most current Google Doc for the correct notes. All right, so read the problem again. So we need a picture with variables, right? The next step in related rates is draw a picture with variables and identify your d what, and then set up a formula, equation, expression that relates the variables in the numerators of your d what. So here we have the pitcher on the pitcher's mound, and he throws the fastball, and we know now that it travels at 132 feet per second, And so we want to know how fast does the batter need to turn his head, his eyes really, to keep his eye on the ball when the ball is 10 feet away from the pitcher and the batter stands 2 feet away from the home plate mat at bat. So we have the pitcher, home plate, and then the batter. So it's looking like a right triangle. So let's draw that real quick. So here's our triangle, but we need to put variables in it. So what's changing? And so let's put where people are. So we have the pitcher is over here on the mound. So for the sake of this problem, we're gonna ignore the fact that the mound is a little bit higher, and we're gonna assume that the pitcher throws the ball straight, that there's no right like curving upwards. And so the batter is over here, so I know this is 2 feet, so this is staying constant. Now what's changing? So we know the pitcher throws the ball, he releases the ball, so then the ball travels towards home plate. So this is changing the distance of the ball from the pitcher. So let's call that h. So we're going to say that's the distance from the ball to the pitcher. And what else is changing? So let's go back to the problem. Urias threw a 90-mile-per-hour fastball. So that's how fast the ball is moving. How fast does the batter need to turn his head or his eyes? So we need to know, when you see the word turn, what does that make you think of? Hopefully an angle, right? So when the ball is, say, over here, then, or there, then the angle from the batter to the ball is different, right? So we're looking at that angle from the horizontal to where the ball is. So we're going to call that angle theta. And so we have a picture with variables, and the thing that's changing is the distance from the ball to the pitcher. So we're calling that h. And so let's identify what do we have and what do we want. So we have the rate of change of the ball. We know how fast that ball is moving. So we have dh dt, which is 90 miles per hour, but we converted that to 132 feet per second. And what do we want to know? We want to know d theta dt when h is, and I changed the 1 feet to 10 feet. When the ball is 10 feet away from the pitcher. So the pitcher's here, so when the ball gets to 10 feet away from the pitcher, we want to know how fast that's happening. So now we want a formula that relates h and theta in this right triangle. So this is why drawing a picture is really, really important, because the picture helps us know what do we need, right? If when we did the example with the cone, oh, I needed the volume of a cone. When we did the example with the sphere, we needed the volume of a sphere. When we did the example with the boat being pulled, we had a right triangle and we needed the Pythagorean theorem. Here we still have a right triangle, but we also have an angle. So here we need likely a trig function. I have theta, I have h, which is the opposite, and then I have the adjacent, the 2 feet. So we're going to use, that looks like tangent. Tangent is opposite over adjacent. So we're going to say tangent of theta is equal to the opposite, which is h, over adjacent, which is 2. And now we're going to take the derivative of this with respect to the variable in the denominator of our dy. So we're going to take d dt of both sides. So both of them are changing with respect to time. So theta and h are both functions of t. So the derivative of tangent theta is secant squared theta by chain rule times d theta dt, because I'm not taking the derivative with respect to theta. If I just wanted d theta of tangent theta, that would be secant squared theta, and that's it. But because I'm taking the derivative implicitly with respect to t, I need to add that in. And then here, 1/2 times the derivative of h with respect to t. So dh dt. And we want to solve for d theta dt, so let's put that in here. So solve for d theta dt, so divide both sides by secant square. Well, secant is 1 over cosine square, so essentially you're going to end up with a cosine square theta over here times dh dt. And remember, cosine square, when you see a trig function like that, square, that really means is the trig function quantity square times dh dt. And now are we ready to plug everything in? So we know dh dt, that is how fast the fastball is moving, which was the 90 miles per hour, but we converted it to feet per second. And then we're using h is 10 feet. So let's see. So we know dh dt. I don't know cosine of theta. So let's bring in our triangle again, because when h is 10, when we're 10 feet away, we need to know what's cosine of that angle. So let's bring our triangle back. Alright, so here's our picture. So we want to know when h is 10. So when this is 10, that's still 2. We want to know how to plug in stuff in here. So we need to figure out what theta is when h is 10. And now notice that the 10 just represents from the distance from the ball to the pitcher, right? So the pitcher is over here, and the ball, when it's 10 feet away, so say 10 is over here, this is the distance. So let me move the 10 a little bit. So this, when this is 10, we want to know the cosine of the angle. So we need to do a little geometry here, right? Because our angle is here. Now, using geometry, when these are parallel lines, when two lines are cut by a transversal, the angles are congruent, so that's still theta, right? So the angle here are the same. And so how do I find then the cosine of theta? So I have, if now using this theta, using the congruence, using that theta, I need cosine to be adjacent over hypotenuse. So that means I need to solve this triangle. Now this is still a right triangle. And here we have a right triangle as well. So let's use similar triangles and try to figure this out. So let's call this x, this distance here. Let's call that x. Now here I do have to say that we have to know a little bit about the game and of baseball to know what this distance is from the pitcher to home plate. And what we're going to use as the distance from the pitcher to home plate will be 60 feet. It's like 60 feet and 6 inches, but just for the sake of making the math a little bit nicer, we're going to use 60 feet. And again, we're ignoring the fact that the pitcher is a little bit elevated, right? The pitcher's mound is a little higher than home plate, but we're ignoring those kind of things. We're doing everything as if everything was flat and just looking at the linear relationship. All right, so let's look at the similar triangles here. And what we have is, so I'm going to draw them slightly separate. So we have the big triangle. So this is 2, and this is not drawn to scale here, 60, right? And then I'm going to have my smaller triangle where this is 10 and this is x. So that's what my two similar triangles. Why are they similar? We need two angles for them to be similar, and we have two angles. Angle, the right angle, and then we have theta, right? Using the geometry properties that when two parallel lines are cut by a transversal, being the hypotenuse, corresponding angles are congruent. So this theta is the same as that theta. Okay, so now I can set up my similar triangles, and I can say then 10 is to 60, right? The vertical leg is to vertical leg as horizontal leg, x is to horizontal leg to 2. And we wanna know the value of x. So because that's our adjacent. So I can say then 20 over 60 equals x, which that reduces to 1/3. So x is 1/3. And so going back to this triangle, so let me draw it again over here. There's a lot of drawing of triangles here. Pretend that that's a right triangle. Looks like a witch's hat, but just bear with me. So that's 10. Now I know this is 1/3. And I want to find cosine of theta. And I know cosine is adjacent over hypotenuse. So far I know that this is going to be adjacent, which is 1/3. So what about the hypotenuse? So now I need to use Pythagorean theorem there to find the hypotenuse. So I know leg square plus leg square is hypotenuse square. Let's call that C. So that means that the hypotenuse is going to be, take the square root of both sides, it's going to be the square root of 1/9 plus 100 is my hypotenuse. Get a common denominator and reduce here. So common denominator is 9. So 9, multiply 9 over 9 over here. So 900 plus 1 will be 901 divided by 9. Properties of radicals allow us to break up the square root over 3, right? The square root of 9 on the bottom becomes 3. So this is our hypotenuse. Phew. Which means then that cosine of theta is adjacent, which was 1/3, over hypotenuse, the square root of 901 over 3. So those 3's end up canceling out. So I have cosine of theta is 1 over the square root of 901. Holy moly. Okay, so what happened? So we had the pitcher, home plate, pitcher's mound, home plate, and the batter. And so because the ball is not quite all the way to home plate, right, we could do it also this problem, like what if, you know, when the ball reaches home plate, what's the angle? How fast is the angle changing? And then that will be just one triangle. But here, because we're looking at when the ball is a certain distance away from the pitcher, we have to bring in those similar triangles. So going back over here to what we had for d theta dt. So d theta dt, the rate of change of the angle, is going to be 1/2 times cosine of theta square. We just found cosine of theta to be 1 over the square root of 901 times the speed of the ball. The ball is going at 90 miles per hour, but we converted that to 132 feet per second. And so simplify all of that. So what do we have here? 1/2 times 1 over 901, because when you square the square root, those cancel, times 132. And so I can reduce my 2 with the 132. What's that? 66. So d theta dt is looking like it's 66 over 901 radians per second, which ends up being, when you convert it to a decimal, round to 3 decimal places, it will be 0.074. So that will be what our d theta dt is in radians per second. You might convert that to degrees just to see how many degrees, right? Sometimes when it's like about turning body parts, we want to think about, it's easier to think of it in degrees. So what's 0.074 in degrees? There are 180 degrees in pi radians. So what does that become? So essentially a little bit more dimensional analysis here. So times 180 degrees over pi radians. So this is radians. So then my radians cancel, and so you will have 0.074 times 180 divided by pi. So if you convert it to degrees, d theta dt is going to be about 4.2398. So we can't really round to 3 decimal places, so 2. So 4.24 degrees per second. So that's a pretty small angle, right? So then that's with that fast of a ball, that angle has to be pretty spot on to be able to keep your eye on the ball. So that's what this problem is. So there was a lot going on in this problem, and it is one of my favorite problems just because it's realistic, and with situations like this brings in a lot of information, right? We need to know some geometry, we bring in similar triangles, and then trig is involved, and there's just so much going on with this problem. Now, just for some reference, the human threshold is approximately 44 degrees. So the human threshold for eye rotation, and you can probably look that up. And here there was a bit of I asked about turn his head. Now the threshold for turning the head is 90 degrees, right? You can only turn your head one way or the other 90 degrees, so that will be the threshold. But we're really kind of looking at also the eyes. So when the batter is looking at it, so I was kind of focusing more for this problem on the eyes rotating, and so looking at that angle. So there's a lot more involved. I just wanted to kind of make this kind of fun example because it also has so many things in it that we'll see as we go into other chapters. This is the first one that requires the use of similar triangles, and as we move on to the next chapter, chapter 4, and doing more applications using derivatives like optimization, we're going to be making a lot of use of similar triangles. So I kind of wanted to bring this in to kind of review some of that geometry that we may have forgotten, or just refresh that kind of geometry, and then making a lot of use of Pythagorean theorem with trig functions. So this problem kind of had it all. It may not be like a real life accurate, right? Because as all the things mentioned, the pitcher's mound is a little taller, and taking into account also the dimensions of home plate, and so there's a lot of things that were kind of wishy-washy in this, but I wanted to show the different concepts that are required in this problem, right? Drawing a picture with variables, and then using similar triangles, using Pythagorean theorem, using trig, using implicit differentiation. So this problem kind of has a medley of lots of concepts that we've been working with. So that's how I'm going to end related rates. Contact me if you have any questions, and if there are any questions that you have pertaining to these problems and what assumptions I made, then let me know, because some things you may be like, well, but that's not really how things are. Yes, there are a lot of assumptions being made in this problem. So we're just kind of assuming a linear relationship between the pitcher and home plate and the batter. And so kind of like that nice little right triangle without taking into account, again, the mound, that the ball has a curve to it and all that other stuff. So anyway, contact me if you have any questions.